about these things. First, at the beginning I will go quick, because you know very well the impact of art, both for treatment. We know that the life expectancy now has changed. So now it's almost similar or comparable to someone if you treat him well and early. So life expectancy should be. And this is true also in terms of death. So one thing is life expectancy, but the mortality went down. Also, this is a global mortality curve, and it includes, of course, Africa and some resource-limited settings. But in Italy, really the mortality is very small. Although AIDS patients still die. We have patients that are still dying of AIDS even today, because they went through 25 regimens and they are failing, and they had, and actually our patients are now dying for hepatitis and for some comorbidities. Anyway, this life expectancy also changed. This is a very moving slide that, you know, when this is actually the life expectancy in Africa. And then in the year 2000, Mauro was remembering the Durban conference. At that conference, actually, the issue of access to antiretroviral was raised, and we started to bring drugs there, and this resulted in their life expectancy coming back again. They lost 30 years, you know, in the initial times of HIV epidemic. And of course, we know that mortality now is linked to art coverage. So we know that. You know very well what happened with treatment. Now, with prevention, you know that also we use, you know that there are a lot, I mean, we call it a kind of the prevention toolbox. So I'm not going into this. I spoke about this in Gramado. How many prevention methods we have that are not antiretroviral based, but we also have a lot of things, of tools using antiretrovirals. And this is Fauci's slide that I picked from Vancouver, and that's an extraordinary example of treatment as prevention that really works. And still, you see that still we are a little far from zero. I don't know how many kids, infected kids, are born in Brazil today. In Italy, very few, but still we have some infected kids. Anyway, that's a great success. And then we have PrEP. You know, you can use drugs to prevent infection in for non-infected patients, and this is something that is definitely working. It's not allowed or let's say licensed or reimbursed everywhere, but it works. We know that. I remember this trial because it was presented in Rome. You know, I chaired this IS conference in Rome in 2011, and that was the trial that was presented there. Actually, it came out exactly in July, August 2011. So this is a trial that proves, you know, that treatment can also prevent, if a person, an HIV infected person, is treated, the probability that he transmits is reduced by more than 90%, and so that's an incredible result. And now, again, we know that antiretroviral therapy is good, both for treatment and for prevention. And actually, even we have some proofs that incidence, so the new infections, decrease in countries where there is a high coverage of antiretroviral. This is Africa, mainly. But it's not zero. It's not zero. So now that we have the proofs, that treatment works for prevention, and also there is some clinical benefit, I still say some, maybe we can discuss this, because the benefits are there if you treat very early. Let's say that the numbers are not immense. It's significant, but it's not huge. You don't have 200 events versus 5 events. You have 5 events versus 10 or something like this. So in any case, the proof is there that if you treat early, you have a personal benefit, also above 500 CD4. So with this in mind, now all the guidelines in the world, even the WHO, are changing to treat, the treatment is allowed. The start of the treatment can be done also in patients irrespective of CD4. This doesn't mean that everybody that is infected will be treated, actually, because you know that the majority of patients don't know that they are infected. So we'll touch this just in a second. So why, with this great success, because it's a great success of antiretroviral therapy, why we still need to find something else, say a cure, for example. And that's a mix of reasons. Stigma is still there. So if you are infected, even if you are treated and you have undetectable viral load, you are still an HIV positive. And stigma is there, and criminalization is there, particularly in some countries. So, of course, now with hepatitis C, for example, that you have easily curable, of course, you are not infected anymore. So you are not anymore an hepatitis carrier, let's say. But for HIV, even if you are well treated, you're still an HIV positive. And then we know that there are some comorbidities associated with HIV and also associated with the aging of the patient, actually. But some are linked to the inflammation. A few of our friends made a career on inflammation. What I think is that inflammation actually is true. It's a true phenomenon in HIV, but it cannot be hyperinflated, let me say, because even in hepatitis we have inflammation. In all the chronic diseases there is this. But anyway, our toxicity is now getting better, but still we don't know the long-term toxicity, like 25 years. You know, if we have data on, let's say, mid-short-term toxicity, but if we think that a patient have to be, that he is 25 and lives until 70 and has to take the pills for 35 years, then, of course, despite the fact that the new drugs are less toxic, it's a concern for a clinician. Then the other problem is access, because we will see, I mean, access is not universal. We would like to have universal access to art, but it's not actually true. And retention in art is very difficult. You know this very well. And now that we are treating everyone, even these patients that are with very high level CD4, retention is even more complicated. And this is what I see when I treat my patients in Africa, because some of them that are well, they say, why should I take this pill if I feel well? But this is true also for all human beings. For example, I take a statin since 10 years. They say it's anti-inflammatory. But I always forget. Actually, today I forgot, and yesterday too. Because I'm okay. I'm well, so I'm not. And even the patients that have been, let's say, ill in Ethiopia, where I work very often, when let's say the index disease or the tuberculosis went away, and they are back on health, let's say, they stop. So I say, why did you stop? Because I'm cured, because I'm okay. So it's very difficult. Now, say that we treat a patient with 800 CD4 that is perfectly well, and you say, no, you have to take this pill every day. It's not easy to convince him. You say, no, you will die of inflammation if you don't. And this is what they tell me in Africa. They say, when? I say, I don't know. So I said, let's wait. So anyway, in addition, some of these drugs, you are well, you take a combination and you feel bad because you have some side effects. So they say, hey, you are harming me. It's difficult to explain that I'm saving their lives because in the immediate, they are worse than before. Anyway, it's a long story. And then, of course, the economic burden. Now, you know that in the new Sustainable Development Goals that will be signed in New York now in September, you know, there are new development goals that substitute the Millennium Goals that actually did something. Some of the Millennium Goals that should be another talk. I have it actually. So if you want, we can talk about this. Some of the Millennium Goals were reached, or at least one of those is the HIV Millennium Goal. Actually, we did well. It changed the world, in a sense, our battle against HIV. But now we have the Sustainable Development Goals. It's a long list, and actually I'm preoccupied because now there are 17 Sustainable Development Goals with a lot of things inside. I don't know how the world will cope with this. But anyway, so one of the goals is to end AIDS by 2030. Fantastic thinking. I mean, it's nice. It's nice. I mean, let's say but it's quite aspirational. Let's say that it's an aspiration. So it's good to have aspirations. It's good. I want to live forever was singing the rocker. And UNAIDS actually invented a kind of strategy to reach that goal through the use of antiretroviral treatment. Because we know that actually, as I said, antiretroviral treatment should decrease HIV incidence, and slowly, one of the thinking behind this, that I'm also responsible a little bit because I've been in a couple of these meetings with the CDB and our friend, and I remember that my big friend, Joop Lange, you know, our colleague that died in the plane going to Malaysia. Actually, I had to have dinner with him that night, and we were there and we were looking at each other saying, hey, where is this, the other 10%? I mean, where? And he said, maybe the Italians took out because he was very, very, so we had some fun. But anyway, let's say that the idea is good. You know, the idea is that if we are able to, let's say that we have 40 million infected in the world, and we are able to diagnose 90% of those, and then 90% of those we put on care and treatment, and 90% of those are fully suppressed, then the model, because I'm a little scared of models sometimes, you know. Models are fantastic, but models is one thing, reality may be different. They say, I mean, this may help. Let's say that I don't disagree that this may help a lot. But what I say, I think that you concur, that treatment as prevention, that is now, you know, the Bible, let's say, of us, will not be able to do the job alone. So this is, I'm pretty sure. And actually, I wrote this, sorry, this is a previous article I wrote in May, something like this, in Lancet HIV, putting some issues on these 90s. It's called End of AIDS. You find it online. It's free, and so there are a few things to let's say to fix with these 90s to make them work. The other day I wrote this, Mauro C, and you sent me a very nice message. I said, addressing barriers to the end of AIDS by 2030. And actually, you know, Mauro, something strange happened with this article, because you read it and said, you texted me and said, he's very well. Actually, it's true. I wrote it in Greece. I was in an abandoned island, so I had some time to think. And so I just wrote this because Lancet asked me this. And now there is, just these days, because he's out since a week, this day I had a lot of reactions. The Global Fund put it in the first page of their own page on their website. You can find it. Yes. And with a big commentary. And then Gates called me, not Bill. but his guys, I mean Emilio, he said, you know, this is exactly what we think. Because I said that we need more than treatment as prevention to end the epidemic. And I put a number of challenges. The first is scientific. I said we need a vaccine. Definitely we need a vaccine. And I tell you why. Because, first of all, the incidence is terrible. It's still dramatic. The number of new infections yes, they decreased, okay? They decreased over time since 1995 from 3 million to 2 million, which is fantastic. 1 million infections per year, I'm talking per year, averted is a great story. But still 2 million per year is more than the number of patients we are able to put on treatment each year. We reached 15 million, you know, great success of access. And, but then it took 15 years to put 15 million on treatment since the year 2000. So make a calculation, it's 1 million per year. Okay, recently we did better, but on average is 1 million per year. And if we have 2 million new infections per year, that's I mean, the mathematics tells us that something may be wrong, you know, that we will not be able to keep going. And the terrible thing is that there is a very low awareness of HIV status. So treatment as prevention is great if everybody knows. But this issue of the iceberg of the unknown infected is a giant, you know, it's a mountain. You can say whatever you want, you can treat at 3,000 CD4, but if millions don't know that they are infected, they will never get into treatment and they will never stop to transmit, because they will continue to transmit. They don't know. And the coverage of antiretroviral therapy is still very low. It's the success of access, sorry for this, is great, but still we are very far from being perfect. We are around 40%. And it varies a lot among regions. Look at here. Here is Eastern Central Europe. Those in need, only 20% of those in need are treated. Actually, Mauro, you know that I am in the committee, in the organizing committee of the Moscow conference. You are too. I'm going to Moscow now. You are? Yeah. Okay, so great.
November, October.
I hope they will, yes, I hope they will allow us to get back. I tell you one thing, because Lancet called me today to ask me if I want to go to London to review a new series. You know, they do the series, and this is for the incarcerated people, and I have to review the paper on how they treat incarcerated people in Eastern Europe. So anyway, I hope they allow us to go back, that Putin will allow us to leave Moscow. Anyway, so as a result of what I'm saying, we have an incredible amount of gaps. The gaps start here, and then here. So we are around 11 million suppressed. Okay, so 11 million suppressed. We should have 30 million suppressed. So we are at 1/3 of what we hope. So access, so only 11 million are now treated, and we are around 40% of coverage. So that's very bad of those in need. So how can we think that treatment will curb the epidemic with these unsuccessful attempts we have to coverage? And then there is another final issue, why we need a cure. Let me come back now exactly on the issue. Is that if we really want to follow what UNAIDS say, we will need to put on treatment around 30 million people. And now we are at 11 that are fully suppressed, let's say. And this is incredible in terms of money. You know, just for 1 year, we need $22 billion US per year for this machine to keep people in care and treatment. So consider that this should be tripled. And actually the money that the countries are giving to fight HIV/AIDS is decreasing. So there is a terrible, and this will be forever. If we don't stop this epidemic, this will be 3 times this forever. So, of course, the money is there in the world. You know that. I mean, I don't know, China burned 400,000 billions in a day. So the money is somewhere. But it will not be allocated to fight HIV/AIDS, of course. It's for other things. So I'm talking about the money which is available for HIV/AIDS, and it's not a lot, and it's decreasing because the interest, and this is what I'm saying in my paper, the third challenge, apart from the cure and vaccine, is political, because there is a decrease in, even in the sustainable, sorry if I come back to this, but even in the sustainable development goals, health is a little bit, is a small piece, while the millennium goals that were 4 goals were for health. Now we have a little piece. And also in Addis Ababa, you know, there's been a conference now for financing, for development. Health was not there. Health was not there, just a little paragraph, and without commitments. You know what they say in the Addis Ababa? They say that the countries need to find their own, they need to use their own resources, which is okay. So which is,
where is it?
That's innovative financing. Someone said, no, I mean, you know, Botswana, use your money to save your people. That's very, very smart. I mean, someone smart was there. Anyway, let's see now. Let's go to the cure. I'm sorry for this diversion, but that was as an introduction. This is why we need. Okay, you know this issue is HIV persistence. This is a very, very old paper from Siliciano, you remember the 2003, where he was measuring the reservoirs. And the reservoirs, he was calculating that the decay of the HIV reservoir. You know that HIV integrates into the cells and stays there forever. And this reservoir is long-lived, and it takes like, I don't know, 80 years to decay. So it's above our lifespan. And that's the beginning. Why we thought, or we still think, that to cure HIV will be very complicated, for this reason. And we know that art do not eradicate HIV. That's very, we saw it with our patient before. If we stop art, or art is not working, the virus comes back, even if it's suppressed. So that's trivial, very easy. HIV persists during art. But why? Because actually art doesn't cure alone HIV. It just blocks replication. That's very, very stupid to say. It's the immune system that should eliminate the infected cells, but the immune system is not able to do so. We produce a lot of antibodies during but they don't work enough. Actually, they are not neutralizing antibodies, you know that. So a sera from an infected person cannot stop even the new, like Ebola. The blood of the infected person works to cure the others. Here, not. And the other thing that was quite clear is that the reservoir, the cells that harbor the latent HIV virus, which is integrated, are diverse. There is an enormous amount of different T cells that are infected by HIV, but they are also different from, there is what we call the so-called memory cells that harbor the integrated HIV are very different. We call them stem cell memory cell, central memory, transitional memory, effector memory, and terminally differentiated memory T cells. And all these cells are different in terms of producing different chemokines, responding to different chemokines. So it's not just one population of latently infected cells. It's a huge amount. It's not huge, but it's very different from, and that's one problem. So what's the mechanism of HIV persistence in all these cells? First of all, we have two kind of reservoirs. One, which is small, is called active reservoir. This active reservoir actually is composed of cells that sometimes reactivate and produce new virus. And this is the cause, for example, of the blips that we see sometimes in our patients. Because some of these reservoirs, let's say there is a drawer where the virus is, some of these cells awake and start to produce the virus. The other latent reservoir is composed of cells that do not replicate the virus, that are really where the virus is dormant, and actually they survive for years. And this is why we think, at least, that it's impossible to take out the virus from the infected cells. Actually, one reason why some think that it's almost impossible to take it, and then we will see how we do it, to take the virus out from the integrated virus out from the cells, is that it's a retrovirus, and our cells are full of integrated retrovirus that stay there forever. You know that 10% of our genome is composed of integrated retroviruses, that no evolution get rid of it. So they are there for something. If not, the evolution would have taken out all these retroviruses. Maybe they are good at the developmental stage of the kid, but still our genome is full of integrated reservoirs that stay there. So people say, hey, how can we be able to activate and take out the virus from the latently infected cells? Let's see how we are thinking to do it. Let's see. Actually, some of these cells that are, in a sense, that do not allow the replication of the virus, they can, in a sense, replicate. So they enlarge the reservoir. So the virus is still dormant. It doesn't, but it's the number of cells that may increase progressively. So it's not a stable reservoir. Some cells do replicate, and then the cell actually, you know that the activated cell has a limited lifespan, so it's not forever. But these other cells actually are long-lived, and they sometimes replicate, so the reservoir can enlarge. So the big problem we have now is to understand where is this reservoir, and what actually happens there. We think that on one side we have a latent infection, as on the right-hand side, the green ones, and on the other part of the mirror we have some residual replication. And this is why we think that inflammation and immune activation persist even during antiretroviral therapy. This is why we have proofs, despite what Steve Dick say, that inflammation is ongoing also during antiretroviral therapy. And this is why we see some comorbidities, etc. I'm not a fan of this inflammation thing, but let's say that I am partially a fan. That HIV, that the inflammation is true when the virus replicates, but I'm not sure it's the real cause of the only cause of all the comorbidities that we see with our patients. We believe that the traditional risk factors still have a very important role, and that our patients are prone to these traditional risk factors more than others. So they smoke a lot. So it's a mixture of HIV plus the traditional risk factors. Anyway, this doesn't have nothing to say to do with the cure, but it's something. So what we think is that the persistent viremia that we still see even in the presence of antiretroviral therapy arises from the long-lived latently infected cells. So again, as I said, is that these long-lived cells that by chance reactivate, they are the cause of the persistent viremia that we see even in treated patients. So it's not that the drugs do not work. It's that these latently infected cells sometimes reactivate and produces some virus. So you see these blips. And this phenomenon exists throughout, even during antiretroviral therapy. But what we tried to do in the past is say, hey, if we, instead of giving 3 drugs, we give 5, not as a salvage, let's say, to a patient, let's see if we can decrease this residual viremia. So if we need more drugs, and this didn't work. So they tried. This is an old study, you see. They started, that's 2008. So we said, okay, let's give to a patient, not for salvage, but just to a patient that was controlled. We intensified. Instead of giving 3 drugs, it was undetectable, let's say, and we were measuring the copies and of the residual, let's say. This is the 50 copies. But we know that below the 50 copies, some patients still have this 21, 5 copies, you know that. We don't measure it, but if you have very sophisticated assays, you can measure, and you still find some virus there in the plasma, despite being undetectable. And this is due to what I was saying, the continued replication from the reservoir. I don't know if this concept is clear. And we tried to cut this phenomenon by giving more drugs, but it didn't work. Because it's not because the drugs doesn't work, it's because these blips, these latently infected cells reactivate, and there is no, and unfortunately the drugs cannot do anything. They can stop the produced virus to infect other cells. This, yes. I don't know if this is clear. But they cannot avoid the reservoir to be reactivated. Okay? The virus which is released will not infect other cells because of the presence of the drug. But still, this release is continuous. Anyway, that's... Now, how can we measure? The big problem we have with the cure is that our measure of the reservoir is very rough. First of all, we think, at least we have some proofs, that these reservoirs are mainly in the lymphoid system, mainly in the gut. You know that the gut is where the lymphoid system is, apart from the lymph nodes and the spleen, etc. But the gut is a kind of enormous lymph node. And this is where the reservoir may be. Actually, we did a lot of studies. Some of our patients were so nice to have biopsies. You know, we were measuring their reservoir in their guts. They were really volunteering to, because they wanted to know, and they were curious. And so they accepted to be biopsied, and we monitored the reservoir in the gut during antiretroviral therapy to see if it was decreasing. And actually, it doesn't decrease very, very quickly if we don't have other things. Now I'll tell you what we are trying to do now. So, okay, as I said before, this is boring in a sense. It's just to say that all these kind of, let's say, memory cells, all these types that the transitional, blah, 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 they have different, they contribute differently to the reservoir. So some of these cells are more infected, latently infected, others are less infected. But that doesn't really change the problem. The problem is that we have mainly three problems. The first is that all these persistent cells are in different places. The gut, the lymph nodes, the vaginal and the let's say the reproductive tract, let's say, and the brain. And all these reservoirs are situated in what we call sanctuaries. So it's not very easy for our intervention to reach these four places. I don't know if this is clear. I mean, we know that there is a barrier, for example, in the brain, and we know also that there is when we measured, for example, the viral load in the plasma versus the seminal fluid, we know that there is a disconnect. There could be a disconnect. So that means that the situation of the infection is different. So the first thing is that any future eradication strategies should reach all of this. If we miss one, we will never. Even if we find the cure, we need that the cure goes there. I don't know if this is clear. Then the latently infected cells, because they are latently infected, means that the virus is not expressed, they are undistinguishable. So you cannot say that this cell is infected unless you look at it with molecular biology. But the immune system, for example, is not able to recognize a latently infected cell. There are no markers. You know what I mean? There is not a plata, come si dice, of the car. It's exactly like an uninfected cell. So that's one problem. And the other thing is, as I said before, that the latently infected cells are different. So there are different categories. The transitional, the stem, etc. Those are different cells. So they are not, it's just not one population of enemy. They are different. So those are the three, let's say, general barriers to eradication. Now let's go. So, as I said, the reservoir challenges for a cure is that this is the first thing you have to read, that we have a primitive understanding of targets for intervention. So it's like, you know, a foreign country, you don't know where the bombs are. You don't know where this country keeps their nuclear weapon. So we have a primitive understanding of where the target will be. And also, until now we have a technique we used actually in my lab and on other labs and with JP, is called the tilde. The tilde, which actually was developed by Nicolas Chaumont, is a technique that is able to measure the quantity of virus in latently infected cells. Is the most sophisticated one, because until now, first of all, we used to measure the latently infected cells in the circulating blood. You know what I mean? We were taking the PBMC, and with PCR, we say, okay, how many are infected, are latently infected? But that's, as I said, is not an exact measure, because we are taking just one reservoir, the circulating latently infected cell. That's nothing in comparison to the sanctuaries. And also the technique to measure, the PCR that we were using was not good. So if you want to measure the reservoir, you need to use the tilde. There are now a number of papers out. So let's see now, I'm coming to the point, slowly. The strategies that we are you tired?
No.
No. Okay. So I just have another couple of hours, not more. So now let's see. I talked to you about the reservoir, the problem, we don't know where it is, the different cells, etc. They are undistinguishable, blah, blah, blah. Now, let's see what are we trying to do. So first of all, there are two kinds of cures. One is eradication. Eradication means that the person is sterilized. There is no HIV anymore. No infected cells is no longer there. And this happens for a number of diseases. Hepatitis, it's cured. You cannot find an HCV molecule in a cured HCV infected patient. So that's the best eradication. And we have an example I'll talk about you. And then another possibility is the remission. This means that the patient can live, is almost undetectable, can live without therapy. And we have some examples, very rare. And we are also thinking of how to do it, because it would still be good. The only problem I have with remission is that, are we sure that he doesn't transmit? You know what I mean? Yes. Because say, no, yeah, it's remission, it has a very low copy number. Yeah, but what about his semen? Are we sure that one day, one night, he is not infectious? So that's the problem. And now, let's start with this, with remission, the so-called functional cure. Functional cure. Okay, there's been a number of cases, but we can use just one hand to count them, of functional cures. The Mississippi, you remember the Mississippi, they are called upon the country or the city. Anyway, this is something that happened sometimes because generally in this situation, the patients that had a remission, the few because again it's like a dozen, have been treated very early. The Mississippi baby was, for example, treated after birth, immediately. And we thought to say, hey, if you treat immediately after infection, actually, my criticism was that even if this is true, how many patients are we able to treat 1 hour after the infection? 0.3%, because anyway. But in this case, particularly with this Visconti cohort, and actually this issue of early ART is true for all the memory cells that are infected by the virus in a kind of latently. So it applies to all these latently infected cells. The fact that if you treat very early, the reservoir, the number of latently infected cells diminishes. Of course, but that's very easy to understand. If you stop the war at the border, you avoid that the army spreads into your country. So, and that's true also for the virus. If you stop him with the drugs immediately, it doesn't seed around. It doesn't go to the different reservoirs that he likes. So that's very, in a sense, is clear. But this works in all these latently infected cells. Now, this is the Visconti cohort. You know, these are these so-called elite controllers. You have heard about this, of course. There are a couple of cohorts like this, I don't know, that those are patients that by chance were treated very early. Then they stopped therapy and they remained almost undetectable. Almost. A few zero, but zero means below 50, then 2 copies, 5 copies, but forever. Now some of them are 15 years without drugs. Good, but it's not applicable to, or it's a rare event. It's like those that have the CCR5 mutation that cannot be infected. Yeah, that's a gift because you can be in Rio and go around all night and you are immune. Fantastic. But and Barbarella, yes. I also saw that they closed the help. Yes, yeah. No, I know Rio very well. That's and anyway. So this happened, but let me say that this remission is not really something that can be used, or that is. Now, what we know, what we want really is the eradication, is the sterilizing cure, because it's safer. So now let's see how we can go towards the eradication. So first, we could find a marker that identifies these latently infected cells and knock them off and kill these cells. But as I said before, it's impossible to identify these cells. there is not, this marker is not there. Maybe one day one guy will find this marker, say, hey, this is a latently infected cells, let's kill, let's do something to kill, and then this is another step. But in any case, it's not for the moment. Let's say that, let's take this out. We are not in the position to identify in a person the latently infected cell, either with whatever, vector or immune system. I mean, they hide and they are undistinguishable. Now, kill immune cells non-selectively. Immune cells means those that are susceptible to the HIV infection or are infected, even latently infected. So you can kill everything, like a bomb, a nuclear bomb, and then you promote immune restoration. But this happened one day, once. This is the Berlin patient. This Berlin patient, you know what happened to him, you know that. He was an HIV positive. He got a leukemia. So they treated him as we treat leukemias. Good. It's a bomb. It's a bomb. So we treat leukemia, you know why, how? We just do chemotherapy, total body irradiation, and transplantation. And actually a lot of our patients with leukemia are perfectly well, even if they are HIV. By chance, the donor to this patient was a CCR5 negative. It's very interesting. And he saved this, the Berlin patient, because the patient was, of course, CCR5 positive, because he was infected, so of course he had this receptor. The donor was a CCR5 negative, and the Berlin patient, after the transplantation, became CCR5 negative because he had the immune system of the donor. And actually, he had no virus. And it still is the only. I met him. I met him in Marseille, in a conference of a friend of ours. He was there, very nice guy. No HIV, real. It's true, because they are trying to find, and is really totally HIV free. But it's the only one. And that was a bomb, in a sense. Now, you know that they tried. Now there is also a company that, and actually they presented some data which are actually interesting. They do apheresis. They take out the CD4 of the patients, the HIV infected. They engineer with a zinc finger their CCR5 receptor gene. I don't know if you follow me. Then they make these cells CCR5 negative, and then they reinfuse it to the patient. And actually, in some cases, they had some success. So it has been successful, partially. Let's say, not totally, but they have low viremia, etc. Because they are substituting their CCR5 cells with engineered CCR5 negative cells. So the virus that they have in the body, it has no place to go. Very complicated. I don't see it in Botswana. Down to every, the 40 million, you say, apheresis to 20 million, engineering, so that's. Actually, some friends of ours tried to do the transplant, to redo the transplantation. That, in this case, was an allogeneic stem cell transplant, but actually, it didn't work. So again, that's good for research, but it's not working. Now, let's see if we can interfere with the host determinants of persistence. This, what does it mean? That if we think that this immune activation is that this replication of the latently infected cells is what enlarges the reservoir, maybe we can stop this process. I don't know if I'm clear. People say, okay, let's try to stop this inflammation activation system with some strange drugs, even methotrexate. because methotrexate, you know, it has also an anti-inflammatory effect, and so they are trying by inhibiting some chemokines, still very dangerous, because when you touch this system, this chemokine, lymphokine, you can really, let's say, disrupt the homeostasis of the immune system, and it's very dangerous. So, as I said, this is actually our friend Mauro. These are the slides from our friend. It was at the INRS board. Mike Lederman, that gave a very nice talk. He said it's plausible that some of these strategies may affect the reservoir, but will that be enough to have impact on eradication? We don't think. I mean, maybe it's a corollary, you know, say, okay, let's use these drugs to also close the inflammation that make the circle persist. But you can understand, it's a minor, you know what I mean, is a kind of, so that's the way forward. The way forward is promoting the viral expression from latency and knock off the expressing cells. So we need to awake all the latently infected cells and use the drugs to kill the virus, so the virus cannot replicate, and use other systems to kill the cells. I don't know if it's clear. If we activate everything, the virus will go away, but fortunately we have the drugs. And the infected cells should also be killed. If not, they will continue to produce. I don't know if it's clear. But if they are activated, then we can recognize them. The immune system could recognize them. So it's not, so now they are recognizable because they are activated and they produce the virus, so they have antigens on their. So that's something that we are trying. And let's see how we do it. So, cure strategies. First of all, we have, again, is a summary. I'm going to the end, but the first is to limit the establishment of the reservoir. We saw it, early treatment. That's trivial. That's simple. Better to treat early. The reservoir is smaller, we know. Then, render uninfected cells resistant to HIV is the CCR5 thing. It worked once. Deplete infected cells with a bomb. It worked, but so the only way is really to flush out the latent reservoir, and how we can do it. So the concept is called shock and kill. Okay? Shock means I activate all the latently infected cells and then I kill. So that's the wording, shock and kill. But there are two problems here. One is, can we shock safely? Because to shock, you know, means when you shock, it means that you use something strong. And then after this, as I said before, can we generate enough well-armored defenders to reach and kill enough expressing targets? So we activate, then we have to kill everything. Shock and kill. So is this safe? We'll then be able to have an army to kill all the reactivated cells. Let's see how we do. So first is reversal of latency. This is what we are trying now to do, to reverse the latency. Let me say that I'm scared of reversing the latency sometimes. You know why? Because we have a lot of retroviruses already. Let's see that if we reverse some very important retroviruses by using the reversal agents that I will show. And I'm not sure that we don't get any cancer or something like this. But anyway, let's say that the strategy is reverse the latency. How can we do it? Okay, we use what is called latency reversing agents. Okay, see, this is a latently infected cell. Virus do not replicate. We use these reversing agents. The virus, the cells is now producing recognizable. And of course, we have the drugs to stop the virus, okay? So I'm not preoccupied by the production of the virus. I don't know if you follow me. Because we have the drugs, so it will never infect other cells. Clear? And now what happened to this cell? But we hope that this cell will die because of the immune response. So that's the shock and kill. Here we shock, then the virus is blocked by the heart, and the cell dies either by itself, because you know that an activated cell, in any case, has a limited lifespan. It's not a long-lived, as I said, I told you before, 70 years to die, you know, memory cell. Now it's no longer a resting memory. Now it's an activated cell, so she has a limited lifespan. Okay, those are what we are using. I'm saying we because we are a family. Yeah, we love each other actually, quite. So, except in our own countries. No, that's true. We have a fantastic friendship. Sorry for this, and that's a pause, a little pause. Because the first hour passed, so now we have an interval. So actually, we have a fantastic friendship between us, working in this field since like 30 years. So I know, for example, that if I have a problem, I can call Mauro. No, really, even in 5 years that we don't, I say, Marco, I have a problem. I say, okay, I'm coming. That's true. This is true for him, for others. And we have a fantastic friendship between HIV experts in different countries. If I call my colleague in Milan, I'm not sure he's coming. Now, the pause is finished. Now, what we are using are this strange name. And actually, this in vitro, if you put the latently infected cells in vitro, you put this, boom, the virus comes up. So it's true, they work in vitro. Now, let me say that they use it also in vivo. One of the first is this vorinostat. Vorinostat is an anti-cancer drug. Would you take an anti-cancer drug? Yeah, it's not a very active one, let me say, because. But actually, is one of these HDAC we call histone deacetylase inhibitor, and it's used in some forms of cancer, not alone. But anyway, it worked also in vivo, so it reactivates the latently infected pool. And we were able to see it in fully suppressed patients. You give this drug, boom, the virus comes out. From where? From the reservoir. So it means that this virus was awakened, and the cells were awakened by these products. So the shock is possible. Let's say that we are trying to use different compounds. And it's published, you know, all 2014, 2015 papers. So it's working. And I mean, this is one. Yeah, this is David Margolis, HDAC inhibition for the disruption of latent HIV infection. There are a number of these. This is a year old, but so it works. The shock. Now, let's see the kill. How we can do it. Actually, we don't have only drugs to activate. Also, some chemokines have specific effect, like interleukin-7 and interleukin-15, they do the same. They activate transcription. But as I said, using these lymphokines is dangerous. A little bit like the other drugs. I don't know which is more dangerous, let me say. And then, so now let's see the kill. After activation, okay, that we see that it's possible, how can we facilitate the clearance of infected cells and enhance immune control? That's the question. Okay, immune-based therapy. This is what we are using after the shock. And first of all, there are a few problems. The first problem is that you know that the CD8 T cell response is weak. If not, we were not here talking about HIV/AIDS. We have a cytopathic immune response that doesn't work well during HIV infection. It works for a while, then is exhausted. As I said before, the antibodies are not neutralizing, and the CD and the cytotoxic cells are not functional. And this is why this virus is very happily with us. No, not really, because who cares? No antibodies, no good antibodies, no cytotoxic activity, that's it. So that's a problem. We have a CD4, a CD effector cell that is weak because they are exhausted during chronic infection. And this is true for many diseases, for many chronic diseases, not only true for HIV. We know that during an acute infection, the antigen is cleared. The antigen is cleared even by antibodies. You follow me? Then there is no circulating antigen for longer time, like influenza or other diseases, also where the cytotoxic cell work. The virus at the end, or the agent, disappear. In the HIV infection, the continuous persistence of the antigen exhausts the T cell. I don't know if this is clear. This is a phenomenon that is clear also for in other diseases. And what happens is that these cells put out the exhausted CD8 cell is recognizable by some, let's say, blocking receptors, PD1, for example. So when the cell is exhausted, they took out a kind of white flag, say, I'm exhausted, I'm no longer active, okay? Now, what some understood that if we block this receptor, the PD1, then the cell is functional again. And this is what happens with what we call is the immune checkpoint. Look at this phrase, because I had also to learn this, but this is a new wording. You know, the immunologists always invent new terminology. So the immune checkpoint blockers are the solution, because if we are able to block this immune checkpoint, then the cells start to work again and to clear the infected cell that is now recognizable because it's activated. It's been shocked. I don't know if it's clear. The cell now has a kind of, the infected cell as a flag. We make the immune system working again, and that's make a difference. And this approach is used in cancer. You know, the revolution of these monoclonal antibodies, anti-PD-L1, in cancer. You know that they increased the survival of lung cancer by 50%. That's yesterday. And this is an immense field, also for the pharmaceutical industry, let me say, that found another treasure because now there are 2 or 3 companies that have this, anti-PD-L1, pembrolizumab, those are all monoclonal antibodies. They cost a fortune, but really in non-small cell lung cancer, which is deadly disease, it worked. And so it's a revolution, and we are using it in HIV, together with the shock. And this is something I'm doing in my lab, actually. I'm working with Geppi Pantaleo in Lausanne. This very big friend of mine. He will call, if I call, he's Italian, but he's in Lausanne. That's, so if I call him, he comes. And anyway, we are working on this on monoclonal antibodies against PD-1, and actually we are trying to we are constructing the B-specific antibodies. You know that now it's possible to have those are constructed in the lab. You do monoclonal antibodies with two targets. They target 2 different epitopes. And it's very interesting because actually with these bispecific antibodies, you can also carry, and this is the other thing we are doing. We are using this cell that has on one side, it fits to a receptor on a cell, and on the other sides of the antibody is linked to, for example, a receptor for the NK. So it brings together the effector cells to the target cell. So it's kind of bridge. He has on one side, he recognizes an antigen on the cell, and on the other side, he recognizes an antigen on an effector cell. So he can bring, for example, in this case, this is a NK arming bispecific antibody. So we think that we can bring the soldiers towards the target that in this case could be an HIV infected cell. Anyway, that's so this is one of the possibilities. The other possibility is improve the T cell response with immunization. So here we make stronger the immune system in a general way, like using the anti-PD-L1. Okay, so that's non-specific enhancer of the strength of the immune system. Is what happened in these cancers. Anti-PD-L1 is not specific. It just make the T cells again working. I don't know if this is clear. The other possibility is that we can actually immunize or strengthen the immune system by specifically directing him towards the infected cell. And this is one thing that we are trying to do with therapeutic vaccination. Now, therapeutic vaccination has been abandoned a few years ago because we thought it didn't work. You remember we did some trials with therapeutic vaccination. Now it's coming back to age, because now because we know how to shock, now we need to kill. And the only possibility would be to arm again the immune system against, and arming it very specifically against the HIV infected cell that we have been revitalizing. And this is a project that we have, again, with Lausanne. We had just won a big project on vaccines with the European Commission. It's called EVA, European HIV Vaccine Alliance. And you see, we are a lot. I'm here. and I'm in charge of the therapeutic vaccine platform. And what we are doing, of course, is generating de novo HIV-specific immune responses, because in the past we thought that was unuseful. It didn't work to cure HIV, at least to control HIV. It didn't work we already had the drugs. The drugs worked much better. I don't know if it's clear. Now for the cure, that's a different story. I don't know if I'm... So now we are trying to revitalize and arm the immune system towards the infected cells that we, of the reservoir, actually against the reservoir. And for example, this is one of the trials we are designing. We will vaccinate with, we have different candidates, DNA vaccines, etc., to vaccinate a person, which is infected, of course, and then we use a reservoir mobilizer, which is the shock, okay, plus the immune modulators, the anti-PD-L1. So first the patient is vaccinated with a sequence which is conserved. So we arm his immune system. Immune system is ready to go. Then we shock. So the latently infected cells are alive, producing virus, and recognizable. And then our immune cells that we armed with therapeutic vaccine will do the job. And then we will have to check, and this is one of the problems, that this happen by stopping antiretroviral therapy. This is the only way, actually, to see that something happened. You know what I mean? So we need to do these strategic treatment interruptions to see if the virus has disappeared. Let's say, to what extent the virus has disappeared. And then now I talked about strategic treatment interruption because there are a lot of ethical challenges in the research for a cure. So what's the first? I mean, the safety of the drugs targeting host functions in patients on very safe regimens. Let's say that you are a perfect person on, let's say, dolutegravir or raltegravir, one inhibitor, with few side effects, fully suppressed because you have been treated well from the beginning, etc. And you have a life expectancy of 60 years. Yes, you have to take the drugs forever. But people live with this. Now it's easier. We are not taking D4T, correct? And so say, hey, come here, I will try to cure you by giving you cancer drugs. So it's not easy, you know, to have volunteers to say, hey, I'm perfect. It's the same thing that I was saying for Africa. Say, hey, I'm well. Don't cure me. I'm perfectly okay. You know what I mean? I don't infect others because I'm at zero. So, and then also we need to make the treatment interruption to test if it works. To say, hey, no, don't stop. Why are you stopping my drugs? I don't know if you are doctors, so you understand that it's very difficult to convince a patient to get into these trials. And then, let me say, if a cure is found, that's another ethical dilemma. You see how complicated it may be. Shock, kill, therapeutic vaccination, anti-PD-L1. Will it be applicable to the millions infected in the world? Maybe let's say that we find a cure. Maybe you can do it in Rio, not in Manaus. You know what I mean? Because it's expensive. I don't know. Yes, of course, when a patient is cured, you save the money of the drugs. Okay? So in a sense, what we were saying before could be good. You know, it could be a good deal. Say, you know, what's the cost of the drugs? $10,000 times 20 years is this amount. If the cure costs $30,000, that's a good deal, you know. But anyway, apart from the cost, are you ready to do this in Rwanda with the anti-PD-L1 in the bush? So that's one of the ethical challenges for a cure. We need to find it, and I'm finished. I forgot to talk to you about vaccine, not the therapeutic that we will use for cure, but the prophylactic vaccine, because one thing that I said in my paper, I will have some enemies, you know whom, tomorrow, apart from the fact that I said that treatment as prevention may not be sufficient to curb the epidemic, this is what I wrote, we need a vaccine. We definitely need a vaccine. Because with these 2 million that are infected every year, we will never keep pace with this epidemic. We need a vaccine. And actually, I can tell you that a preventive vaccine is closer than what thought a few years ago. We are almost there. It's incredible, but it will be there, I'm sure. Our project will make it. No, I'm joking. But you know how they went to this? By using the monoclonal antibodies again. And through the production of monoclonal antibodies towards certain parts of the HIV virus, I make a long story short, and this is really June 2015, June 2015, this is very recent. Now, it has been possible to construct what is called a trimer. So a part of the virus, of the envelope, which is stable and conserved. So this is the future. That this trimer, which is called stabilized trimeric envelope, that actually is able to elicit deneutralizing antibodies that our body on its own is not able to do. You know why we are not able to do the neutralizing antibody? Because the antigens that elicit the neutralizing antibody are hidden into the envelope. So the virus don't show these epitopes. It's very smart. So it just shows epitopes that induces antibodies that are useful just to make the ELISA test. These are there for nothing. The antibodies that are tested by the ELISA are passengers. The good ones, those, in fact, only a few patients in the vaccine, you know the vaccine trials that have been tested in Thailand, that was an unsuccessful trial because he protected only 20%. So a vaccine that protects 20% is a no vaccine, you know that. But then they said, why this 20% was protected actually? Because it was an unsuccessful trial, but with some very interesting results. So they went there and they looked at these protected ones that definitely went in contact with the virus but did not get the infection. And they discovered that these patients were able to do deneutralizing antibodies. And so taking the neutralizing antibody, you can then look at on the other side of the antibody and look at the epitope. You know that you can reverse. And now we know which epitopes induces neutralizing antibodies. So that's it. This is it. And we will try to use these trimeric things as an immunogen to induce monoclonal neutralizing antibodies that will protect, that we may be protective. Of course, there is a lot of work to do, still to do a lot of trials, but it's really something that is promising. The situation has changed. And also what I say in this paper, and that's my last slide, is that even a vaccine with this not 100% protection, together with the treatment, may be synergistic. Because if a lot of patients are treated, then you reduce the infectious reservoir. It's like the contrary of the herd immunity. You know what I mean? That if the number of potential infectious patients is reduced, then even a vaccine that do not protect the other part of the world, not at 100%, but if may be synergistic. So you may not need a 100% protective vaccine, but even a 60% plus the drugs given to the infectious people may change the situation, and this may curb the epidemic. We need a vaccine. And what I said at the end is something that this is a very old thing. Is not mine. Is Winston Churchill. You know, I said that a mistake would be to consider that the beginning of the end. And what I think is that we are just at the end of the beginning, so a long road to go. You know who pronounced this phrase? You know, is Winston Churchill after the first, when the Germans tried to invade England. You know, there's been a terrible battle in the air with the, and actually the Germans couldn't get in. And that was a victory in a sense. So everybody was celebrating this victory. But that was 1943. And he was right, because everybody would say, hey, we won the war. He said, no, that's not the beginning of the end. That's only the end of the beginning, so we will have many years to go. And actually it was true, because that was not the end of the war. It was just a little piece, a little brick towards the victory. And this is what I'm trying to say this. So I'm sorry I was a little long, and I hope I didn't, oh, sorry, I need to say thank you. That's it.